So the next situation or next things which we are discussing is disappearance of isolated vertices. What does it mean? That means when the isolated vertices will be disappear from the GNP graph model. So is that the disappearance of the vertices in GNP has a sharp threshold at ln upon n. And at this point, the giant component is also observe all small components, and with the disappearance of isolated vertices, and in this situation also, if the disappearance of isolated vertices also, that is a probability that the graph will become connected. Okay, so this is the actually a theorem, and we are trying to prove this theorem that the disappearance of isolated vertices in GNP has sharp threshold of ln n upon n. Let us discuss the proof of this. So obviously what we need to use to prove this one, we need to find out, we have already P in front of us. Now how to get this P, it's very interesting, and it is lots of intuitive idea you require to establish or come across that what should be the value of P, so that there is isolation of or disappearance of isolated vertices. But we have the advantage is that we have this value of P in front of us. So we need to find out, this is the P, we need to have C, so that if the value of C is greater than 1, then at most surely does not have the property. If C is, sorry, if C is greater than 1 and C is less than 1, that it has at most surely that property. So that is our objective, to see that if C is greater than 1, the expected number of isolated vertices should goes to 0, and C is less than 1, then the expected number of vertices as goes to infinity. So let us consider, let X be the number of isolated vertices in GNP graph model. So I'm just saying X is the random variable and it is a number of isolated vertices in GNP graph. Then what will be the expectation of X? Can somebody tell me what will be the expectation? What does it mean of expectation of X? X is a number of isolated vertices. So what should be the mean of expectation? Expectation should be, anyone? No vertices are, everyone is connected. No vertices are connected. Okay, so in that way, either the every vertices are connected or no vertices are connected. Which one is expectation? Isolated vertex, you know what you mean by isolated vertex. That means a vertex is having no other vertex connect to that, or I can say a degree of that vertex is 0. That is known isolated vertex. So what is the expectation of isolated vertex? That means that every vertex is not connect to any other vertex by an edge. That means if I want to say that this vertex is not connect to this vertex, then what is the probability it is not connecting? The probability of connecting is P. Then what will be the not connecting? Will be 1 minus P. Okay, so this first vertex is not connect to this vertex, is the probability is 1 minus P. A P is the probability which is connect to one vertex to another vertex. How many such possibilities are there? So there are n number of vertices in the graph we have. So this vertex is not connect to other n minus 1 vertex. So that's why it is 1 minus p raised to n minus 1. And total there are n number of vertices. So that's why it is into n. So this will be the expectation of x, which is isolated vertices. Number of isolated vertices. Now, since we believe, that means it is actually given the threshold to be ln upon n. Consider the value of p is ln upon n. By first moment method, we have to establish that the expectation should goes to 0 as n tends to infinity. So that means limit of n tends to infinity expectation of x. Here the value of p we can substitute. That will gives me limit of n tends to infinity n into 1 minus ln n upon n raised to n. Now, sorry, we have taken this p into c into this. So I'll just take c into ln n upon n. Now we will use one of the identity which we already discussed into the or I can say, so one of the identity which might be we have used previously also when we are discussing the higher dimension data, which says that the 1 minus x is less than or equal to e power minus x. So 1 minus x is less than or equal to e power minus x. If I can use this one, and for large n, here if I can use that, so what is my x? That is this ln n upon n, c into ln n upon n. So I can say that therefore limit of e of x as n tends to infinity is equal to, we have ln n, that is n into 1 minus c into ln n upon n raised to n. This we have, and if I can use that, means this property, that is 1 minus x is less than or equal to e power minus x. If I can use this one, and here this is the value of x, if I consider, then this will be the less than or equal to ln n tends to infinity n into e power minus, this is x, c into ln n upon n whole raised to n is already there. So finally what you can have, this is equal to limit n into e power minus c ln n. as n tends to infinity. But what will be the e power ln of x base e? That is x. So using this, we can write down this is limit of n tends to infinity n into e power ln e base power n minus c. So that is instead of x, as per this one, it is n power minus c. Here I have used actually a log b will be log of b power a. So I've used this minus c as a, and that goes in the power of n. So that's why this is equal to a limit of n tends to infinity n into n power minus c. So that's why this is limit of n tends to infinity n raised to 1 minus c. So what does it mean of this? It means that if the value of c, which is greater than 1, that means more than 1, then this will tends to 0, because in that case this n raised to negative power will be there if the value of c is more than 1. If the value of c is less than 1, then expectation will goes to infinity. So what we can say, if c is greater than 1, the expected number of isolated vertices goes to 0. If c is less than 1, then the expected number of isolated vertices goes to infinity. If the expected number of isolated vertices goes to 0, it follows that at most all graph have no isolated vertices. So if the isolate means expected number of isolated vertices goes to 0, it follows that at most all graph have no isolated vertex. At most sure that there will be no isolated vertex. On the other hand, if the expected number of isolated vertices goes to infinity, we need to use the second moment argument on other end. If the expected number of isolated vertices to infinity, a second moment argument is needed. So we need to show that at most surely all graph have an isolated vertex. And that is isolated vertices are concentrated for some vanishing, a small set of graph with at most all graph not having isolated vertices. So to discuss the second moment, we need to calculate what will be the variance, or we need to see what will be the relation, if I can use that corollary which I have discussed, that is E of x square is less than or equal to E of x square plus small o of 1. So need to see what will be this. If I can prove that one some kind of this relation, then we can say that a graph at most have an isolated vertices if the value of C is less than 1. So we have considered if it is greater than 1, it is done. For less than 1, we need to prove. So just assume that the value of C is less than 1. Now where we'll write, consider x is equal to I1 plus I2 plus In, where I is an indicator variable that indicate that whether the vertex I is isolated vertex, where II is the indicator variable which indicate whether the vertex I is an isolated vertex. Then what will be the expectation of x square? Now what does it mean of x square? That means it is expectation of I1 plus I2 plus up to In power n, power square. So it is expectation of this. Now what will be this situation? So to understand, if I expand this nth term and its power, let us see what are the terms is containing by this. So for that, let's do some work. Suppose I have a plus b square. Then what are the terms you will have? It is a square plus b square plus 2ab. So you will have a term which having square of a, square of b, and the product of ab. Suppose you have three terms, that is a, b, c square. Then what you will have, it is a square plus b square plus c square plus 2ab plus 2bc plus 2ac. So when we have a three terms, then the answer or the expansion of this one will be square of a, square of b, square of c plus 2ab plus 2bc plus 2ac. Here we have, there are n terms. So can somebody tell me what is the sum you will have here? So you'll have, it is, yes, anyone? Summation I running from 1 to n. I square, because it is a plus b plus c. So it is square of all the things as we have discussed here. It is a square plus b square plus c square. The square of each and every term you will have here. The square of these numbers plus there is another summation which is multiplied with 2 times because it is a product of two numbers, AB, BC, all possible two numbers is there, and AC. So here it is a possibility I and J, I into Ij, where I is less than J. So whatever the possibilities of product of two numbers is appear here. Now expectation of this, so as we are using the expectation of x plus y is equal to expectation of x plus expectation of y. So as per this, we can write down this is equal to the e of x square is equal to summation I running from 1 to n e of I square plus summation I is less than j 2 times e of I into j. Here I have also used that a into x, the expectation of a into x is a into expectation of x. This is also I have used to common out this two. Now what is the value of this I? We know that this II is either 0 or 1, is 0 or 1. Okay, II is 0 or 1. Any one of the possibility is there because either, so what is this x is I1 plus I2 plus In. What is II? Is the indicator of ith vertex is isolated vertices or not. So there are n number of vertices. So if it is isolated vertices, then it will be 0 value. Sorry, then it will be 1 value. If it is not isolated vertices, then it will be have 0 value. Okay, so this I that means each of this I is either 0 or it is 1. Depends on whether the vertex I is isolated. If it is isolated, then it is 1 value. Otherwise, it will be 0 value. Then what you can say about its square? So can I say that the square of this, if it is 1, then the square of 1 is 1. If it is 0, then square of 0 is also 0. So this I square is also 0 or 1. So that means I can say that II square is actually II for every I. This is the situation we have. So that means in the first sum, that means the summation of expectation of I square is actually sub expectation of I. Now we need to see the other. So from this, now if I can say this is the equation 1, therefore from 1 we get the expectation of x square is equal to summation I running from 1 to n e of I plus I is less than j 2 times ei ej. Now this is what? This is nothing but the expectation of x, because I can write down this is as e of summation of I running from 1 to n I using the same situation, and this is 2 times I running from I to j expectation of I into ij. So this is what it is actually expectation of x plus now this quantity. So how many such pair is possible? So there are n number of pairs will be there. So there are NC2 way, NC2 terms will be here. NC2 terms because There are two elements, we need to choose from n number of elements. So there are NC2 terms will be there. So it is 2 into NC2 into I1, I2. So whatever the answer for I1, I2, it will apply to all of them. So this will gives me the expectation of x into n minus 1, because NC2 we know it is n into n minus 1 by 2, and 2 will get cancelled with this 2. So you don't have this. And what will be the expectation of I1 and I2? I1, I2 means the two vertices together having the expectation. Okay, so the expectation of that is 1 minus p, not isolated vertices, and there are 2 into n minus 1 times will be there. There are, because there are two pairs and minus 1. Okay, so this is the expectation you will have. Now the minus 1 is exponental, is counting the edge from the vertex 1 to 2 twice. So that's why we have subtracted this minus 1 here. So what I write is the minus 1 in the exponent 2 into n minus 1 avoid the counting the edge from vertex 1 to 2 twice. So now what we can have from this is e of x square. So we'll divide now. Ultimate goal is to see what is this. As I told you, that is this situation. That is expectation of x square divided by expectation of x whole square. If I can prove that, that will tends to 1, then will true. So now we'll divide this by ex square. So that is ex square upon ex will gives you 1 upon ex plus n into n minus 1, 1 minus p power 2 into n minus 1 minus 1 upon ex square. So this is the things you can have. Now what is expectation of x? The expectation of x we have already calculated. That is n into 1 minus p power n minus 1. So that's why we can have, if I take the LCM here, so it will have e of x square upon e of x whole square is equal to expectation of x plus n into n minus 1 into 1 minus p power 2n minus 1 minus 1 upon expectation of x square. Now we substitute the value of expectation, that is n into 1 minus p power n minus 1 plus n into n minus 1, 1 minus p power 2 times n minus 1 minus 1 upon n square 1 minus p power 2 times n minus 1. So that is expectation of x value we have substituted here. So this can be rewrite as 1 upon n into 1 minus p power n minus 1 plus. So I have divided this quantity by this, and this quantity by this will leads to n will get cancel out. We'll have n minus 1 upon n. This 1 minus p power 2 n minus 1 will get cancelled. So left with 1 minus p power minus 1. This can be simplified as, or can be written as, 1 upon n into 1 minus p power n minus 1 plus 1 minus 1 by n, this quantity. And this will be 1 minus 1 upon 1 minus p. So we have expectation of x square upon expectation of x whole square will be this. Now we'll substitute the p equal to c into ln by n. So putting p equal to c into ln by n upon n, as c is less than 1, we get a limit of expectation of x square upon e of x whole square as n tends to infinity will be limit of n tends to infinity. See this value, it is actually the expectation, because n into 1 minus p power n minus 1, if the value of p is that, we have already discussed that it will be limit of n power 1 minus c, because we have already proved the limit of expectation of x, that is n into 1 minus p power n. So that will leads to this raised to, and here it is actually, let me do it here, otherwise it will have a, so that is actually gives me n raised to 1 minus c plus 1 minus 1 upon c is all, 1 upon n is already there, 1 minus 1 upon n, and then we have 1 upon 1 minus p, that is 1 upon 1 minus c into ln n upon n. Now what will be this? If the value of c is less than 1, and as n tends to infinity, what is the value of this quantity? That is, what is the limit of ln n upon n as n tends to infinity? Here it is infinity upon infinity form, so it is, you need to apply the L'Hospital rule. That will gives me limit ln of n is 1 by n upon 1 as n tends to infinity, and 1 by n will tends to 0. So this value is tending to 0. This value is tending to 0. So that means this whole entire, this side is tending to 1, because 1 minus 0, this is 1 upon 1 minus 0. So this is 1 plus this quantity, as c is less than 1, it will tends to 0. So I can say it is a small o of 1. Small o of 1 means that it is tending to 0. So by second moment argument, we have discussed the corollary. We have discussed that corollary. In that corollary, we have seen that. Let me write that corollary here. So this is the actually corollary which we are going to use. Let x be a random variable with expectation of x is greater than 0, and if the e of x square is less than or equal to e square x, one plus order 1, then x is at most surely greater than 0. This is the corollary that we have, and here we actually got this, the e of x square upon, that is e of x square upon e square x, that is e of x square is less than or equal to this into 1 plus small of 1. So that means by above corollary, the probability that x is equal to 0 goes to 0. That means number of isolated vertices is goes to 0. That means at most all graph have isolated vertices. That means at most all graph have isolated vertices. Thus, what we can say is ln n upon n is a sharp threshold. For disappearance of isolated vertices. So that completes the proof of this theorem. In the next lecture, we'll discuss regarding the Hamiltonian circuit. That means when the graph will have Hamiltonian circuit, or what will be the threshold for that Hamiltonian circuit.